right, so here we are now at our example 2. Okay. And this example 2, there's actually only one standalone example on its own right here. But let's evaluate. It has its own specialty. So how about our function here is 1 over x squared. Okay. And we would like to find, the problem is asking us to find the limits of this function as we are allowing x coming close to 0. And once again, there was no superscript indication, meaning we are getting closer on the x-axis. We're letting x value get close to 0, generally from both sides of 0. Okay, so once again, understanding clearly what we need to do. Now this time allow me to show all my work on the other board right there, and then we're gonna come back here and write our final answer here. But so with our other work, now left hand side table. So I'm going to create a left hand side table. So how about for x values being to the left hand side of 0, how about let's start out with -1. It's on the left hand side of table of 0, and then getting close to 0. So how about -0.1? Okay, and getting even closer to 0. So how about -0.01? And getting even closer to 0. How about -0.001? And getting even closer to 0. How about -0.0001? All right, so about 5 value entries, which is simply good enough. I am going to pause the video and get on my calculation here. I highly recommend that any of you also do the individual calculations on your own, and hopefully our calculations come out agree from both sides, instructor and students. All right, so hopefully everybody had your own calculation, but on our function 1 over x squared, when x equals -1, then function value came out being just +1. Then this entry right here corresponding to input x equals -0.1, we got output value being 100. Then our next one on the list, when x equals -0.01, our output value is about 10,000. Okay, and then our next output value here, okay, so how about 1 million, and our output corresponding to x equals -0.0001 is going to be 100 million. Okay, and so now conclusion here looks, based on our observation, then we can see that it looks like, now hopefully the bottom of my board here is still visible for everybody, but for the function 1 over x squared, now if we're letting x get close to 0 from the left hand side, okay, then once again get 1 over x squared is the function, okay, then looks like these value, now it's this time it seems like we don't recognize any particular value, but instead these outputs value keep blowing bigger and blowing bigger or growing bigger. So you have your right to say positive infinity. Okay, so as x, once again my statement here is as x was getting close to 0 from the left hand side, then our function value 1 over x squared here approaches or getting big and going to that limit being positive infinity. Okay, and so now once we're done with the left hand side limits, we also need to find out the right hand side limit. So I am going to generate another table similar to the one we've just had. So this time, how about for the x column, I am going to choose from the right hand side of 0. How about x equals 1, and then coming closer to 0. How about 0.1, and even closer to 0. How about 0.01, and even further closer, 0.01. 0.001, and here positive 0.0001. Okay, and then with this kind of function, it's actually a little easier for us here to do calculation. So when x equals 1, function output, and I highly recommend you do your own calculation again. In case that you need some time, go ahead and pause my video and then to come back when you're done with your own calculations. And hopefully your calculations will agree with mine. But so x equals 1, function output will be 1. When x equals positive 0.1, function output comes out equals 100. When x equals positive 0.01, function value comes out to be 10,000. When x equals 0.001, function value comes out to be 1 million. And then when x equals 0.0001, function value comes out to be 100 million. All right. And so once again, observing these y values right here, it looks like our function, our prediction here telling us that the prediction here, it looks like we looking at limit of this function 1 over x squared will grow to positive infinity as well, as we were allowing our x value to come close to 0, but from the right hand side. Okay, and so now allow me to get back to our main board here, our other board. So now this function, this problem of ours right here is asking us to find the limits generally when x gets close to 0 from both sides. We tear it down to the left hand side limit, and we found the function grow to positive infinity, and we looked at the other right hand side limit, and we also found out that the right hand side limits, this function also grew to positive infinity. So in the end, left hand side, this function went to positive infinity as we allowed x gets close to 0 from the left hand side, and right hand side 1 over x as our function, it came to a limit being positive infinity as well, and then when x was getting close to 0, but from the right hand side. So keep in mind, infinity has never been a finite number, has never been an actual number, but at least the way how I see it, both either from the left hand side or from the right hand side, your function is growing in the same direction, is going in the same direction. So concluding this, after looking at the two left-hand sided and the right-hand side limits problem right here, we can still generally conclude that as our x value comes close to 0, but generally from both hands, from two sides, then this function goes to positive infinity as our final answer. Now, it is a little early, and we have an entire quarter waiting ahead to consider, to look through these kind of problems. But this kind of problem, now in this particular problem, it stands alone on itself in a sense that the x value is coming close to a finite limit point. So the limit point is here as usual as far as terminology. So we have a finite limit point. So we already learned that it's called, that value there, it's called limit point. But the final overall limits here, instead of being an actual number like you have seen in the earlier examples, here our limit here came to an infinite limit. So this kind of problem we refer to as we're looking at an infinite. Our function generate an infinite limit, or our function had an infinite limit when x came to this finite limit point right there. All right, and now let me erase all that work here, and let's look at our example 3, another example. example 3. Okay. So once again, we are evaluating limits. We're going to keep investigating more and more limits problem. But let's say I'm going to call that part A. I want to evaluate the limits of a function f of x. So now I didn't describe what that function is yet. I didn't define the function. I'm just saying we want to evaluate the limit of this function by letting x get close to positive 3. Okay, but then our function is given as following. So we want to find the limit, but here's how we define our function. Our function is, on one hand, it's minus x plus 3 for if x is less than or equals 3, and our function, on the other hand, is going to equals 1 as a constant value if x is greater than 3. Yes, ladies and gentlemen, this is a piecewise function. In case you need a reminder, your function is broken into pieces. Now allow me to show the actual graph of this function in a different problem, but this is called a piecewise function. Okay, the idea of piecewise function is that if we are choosing an input value that's being less than or equals 3 here as indicated by the function, then the function here is going to be evaluated by this specific formula. But if we are choosing an input value for x which is greater than 3, then we must evaluate the function based on this other formula, which remains as a constant value. Okay, so let's get to it. But on top of that, I simply just now briefly remind about the algebraic operation, how we work with the algebra, the plugging in. But on top of that, here we are finding the limits. Now, I have been emphasizing the whole time so far that please, finding a limit when x gets close to 3 or you get close to whatever limit point will never be f at 3. We're not doing this. We're not doing this. We're not plugging x equals 3 because x equals 3 is a limit point, but we are in this kind of problem, we're in calculus, we're doing calculus work. So when we're doing a limits problem, we're trying to consider, we're looking at x gets close to 3, but we're not going to directly plug 3 into our function. So once again, take that off from your list of works here. Now, let me get back on the other table. Yes, we have to tear it down to left-hand side and right-hand side table values again. And then make a quick estimate. Okay, so our destination point, our limit point in this case is x coming close to 3. So how about from the left-hand side, I'm going to choose 2 is a good candidate, being to the left-hand side. And then I'm going to choose, how about 2.9. It gets closer to 3, but it's still on the left-hand side, And then how about I'm going to choose 2.99. It's closer to 3, our limit point, but it's still on the left-hand side of 3. And then how about 2.999? And how about 2.9999, 4 decimals, and about 5 entry values. That should be good enough for us. All right, so go ahead and pause the video. I am going to also quickly pause the video here so that I can get on my calculation. All right, so now remind yourself that what we're having here is a piecewise function, and these values, now x equals 2 in the end is x equals 2, I need to remind everybody, is less than 3. Okay, so as long as you're picking a value that is less than 3, then you must use to evaluate because the reason I explained this is because somebody at this point viewing this video might still have a little bit of trouble evaluating piecewise function. So here, when x equals 2, it's in the end it's still less than 3. Let me show. All right. See, our function here is piecewise. So when x is less than 3, as we chose with our table of values, then we need to use this upper piece of the function, this upper definition, to evaluate our function. So now when x equals 2, then we need to go minus inputs x, or now minus 2 plus 3. Okay, and so our outputs value here comes out to be positive 1. All right, so hopefully I only need to do a brief reminder here, and then for the rest, hopefully you got yourself into the right track. Otherwise, you can go ahead and pause the video again and get yourself in a proper calculation. But 2.9 is once again still to the left-hand side of 3, or in other words, less than 3. So I have to use the similar calculation. So final output here came out to be 0.1. Okay, and then for the next value, so 2.99, once again, it's still less than 3, even though it's much closer to 3, but 2.99 is still less than 3. So I am entitled to using minus x plus 3. So that gives me 0.0. Oops, had a little bit of typo here. 0.01. Okay, and the next one here I'm going to have 0.001, and the last one here is 0.0001. All right, and so now conclusion now is telling me that, observation here is now telling me that and our function is being piecewise. So for that reason, I'm just going to generally regard to that, hey, our function f of x, and how it was defined was on the other board that you have seen there. But our function f of x here, as we allowed it x getting close to 3 from the left-hand side, okay, then what is your prediction? Go ahead and pause the video and make your own prediction. Okay, so hopefully you had your own prediction. But so I see that I predict, and hopefully agree that my prediction agrees with yours as well. But these values comes to a limit being, what do you think? What do you think? 0. Okay, so that's the left-hand side limits. As we let x coming close to 3 from the left-hand side, then our function came to limit 0. Okay, but let's consider now, let's look at the right-hand side limits. I am going to produce the similar table. The table of values, but this time I am going to purposely choose those values that's on the right-hand side of our limit point. So remind yourself, our limit point here is being 3. Okay, so earlier I was coming to 3 from the left-hand side, but now I'm about to let x values, come closer to 3 from the right-hand side. So how about we can choose 4 for a good start, and we can choose a 3.1 to be closer to 3, and we can choose a 3.01, and we can choose a 3.001, and we can choose a 3.0001. Okay, but this time my function output is going to be quite simple to obtain. Now remind yourself that these values, they are to the right-hand side of 3, or in other words, any of these values, they are, this right-hand side table over here is indicating that our values we have chosen here, they are all greater than or equals 3. I mean greater than 3, strictly. So let's look back at our other board here one more time. In this piecewise function, how it was defined right here, then anytime we are using a value greater than 3, then we are to use this bottom piece right here, to, and that's why the function is called piecewise. So anytime that we're using this, any x value that's greater than 3, then it's a condition. We are supposed to have the output equals constant 1. Okay, and so back into my table of values that's still hanging here. So when x equals 4, which is greater than 3, according to the condition of our piecewise function output is 1. Simple. When x equals 3.1, the value looks complicated, but output value remains 1 again. And here's 1, and here's 1, and here's 1. Because doesn't matter how I choose these values, they are getting close to 3 and etc., but in the end they're all to the right hand side of 3. Or in other words, on this piecewise function, they are these values of x. They're all greater than 3. So I have my right to say that, hey, output's value is defined to be 1. So we have a conclusion. All right, so this time we don't even need to make any prediction, because I predict that no matter how close we come to 3 on this function from the right hand side. So x gets close to 3 from the right hand side. As we keep getting closer and closer to 3 from the right hand side, our function values will permanently remain 1, which is also its own limit on this function. Okay, so now I have to erase all this work right here to make our final conclusion, and hopefully you took notes for your own on this. Okay. All right, so on the same problem here, now with the same function, left hand side of our function f of x being defined as a piecewise function that you've seen from the other board, then the limits from the left hand side when x gets close to 3 from the left hand side will give us a limit 0. But for the right hand side on the same function, when we allowed x coming close to 3 but from the right hand side, our function came to a different limit 1. Ooh, this is going to be bad, because throughout all of the problem we have seen previously, then the left hand side and the right hand side, they all agree to the same limits. This case is the first time you are seeing limits of the function, same function, but the limits here when x gets coming close to a limit point here from the left hand side go to some value, and then the limit of the same function, but then as x getting close to the same destination point but from the opposite direction, the limit goes to a different value. So here, ladies and gentlemen, this is where we consider that our function, generally, when we're letting x get close to this limit point 3 from both sides, this function has a non-existing limit. So my term here is saying does the limits for this function does not exist. Okay, and then so does not exist. For many textbooks, we have that shorthand symbol D and E right here. So the answer to this is does not exist, or for short, capital D and E, like that. But that's how, and this is how it is, how it has always been. Anytime that the left-sided limits and the right-hand-sided limits do not agree, well, you can make a note here. The two-sided limits do not agree, right? Or did not agree. All right, so that's how we came to our first non-existing limit right there. All right, and so now back to my other board again. Let's say we look at part B. Let's introduce ourselves to another problem, another kind of problem right here. But in this time, how about I'm going to look at, so I want to evaluate, we're going to have a given function, and I'll be writing down the function shortly, but we want to evaluate the limits of this function as x is coming to 0. So x approaches 0, or x is getting close to 0, generally from both sides. You can see again that there are no superscript indication. Okay, and here's our function. So here's how we define our function, where f of x is simply that function 1 over x. Okay, so really for short, all this problem breaks down to just one single statement. We want to find the limits of the function 1 over x, where x is getting close to 0 from generally both sides. Okay, and let's find out once again. I'm gonna use the space of my other board to work out the problem, to work out the solution of this problem right here, and I'm gonna come back to this and put the final concluded answer here. All right, so now on my other board, here's how it works out. So our destination point, or our limit point, is x equals 0. This is the limit point. We're getting close to that. I am now going to generate two separate tables again, and we're going to head into two separate works. So I'm going to consider separately my left-hand side. I want to know how my function behaves as I get closer to 0, but from the left-hand side. So here's our table again. I can go, so from the left-hand side of 0, how about I can start out with -1, then -0.1, then -0.01, then -0.001, then -0.0001. And I don't need any more than 5 values here. Okay, and so at this point we can start picking up pace here. We can really pick up pace. But when x equals 1, our function is f of x equals 1 over x. Remind yourself that f of x equals 1 over x. Okay, so when x equals -1, output value surely is 1. This -0.1 on the left of 0 is going to give me -10 for output. This -0.01 is going to give me -100 with the function for output. And this other value here, this fourth value on my table, is going to give me let's say 1,000, and this is going to be -10,000. So I hope everybody or anyone viewing this video at this point is having a prediction for this. But so limits for this function 1 over x, as x is getting close, as I allow x gets close to 0 from the left hand side, this function 1 over x has limit. What's your prediction? You see, the output values seems like they are getting bigger and bigger, but more negative, so further negative, further negative. So this is negative infinity. Okay, and then so we got the left hand sided limit, right hand side limits. Let's look at x here. Okay. I want to come close to 0 as our destination, but this time we're approaching x equals 0 from the right hand side. So a good starting point would be, how about +1? It's on the left, it's on the right hand side of 0, and we're getting closer to 0. So how about 0.1? And then how about +0.01? That's even closer. And then +0.001, and then +0.0001. Okay, and then once again our function, remind yourself, it's 1 over x. So with these values, notice they are all on the right hand side of x equals 0. So when x equals 1, output is 1. When x equals 0.1, output is 10. When x equals 0.01, the output is +100. Now all of these output values are all currently positive. And when x equals +0.001, then we're looking at 1,000, and here is 10,000. Okay, and so once again, we do have outputs, but observing these outputs, values of our function 1 over x together here, it looks like our sequence is growing up. Our value for y is growing up infinitely. And so it seems like now we have a prediction. I can conclude that based on observation, based on prediction, then our function 1 over x, as we were letting x getting close to 0, but from the right hand side, and once again notice how I use my superscript 0 right there, then the function 1 over x comes to a limit being positive. I have to say it out loud right here, positive infinity. Okay, and so in the end, negative infinity. But now remind yourself, the whole learning so far is these outputs, these are outputs, or in other words, graphically speaking, these are the vertical coordinates, the vertical values of your function once you are graphing it. And so think about the y value going negative infinity means graphically your function is going to keep dropping value infinitely and infinitely down. Whereas if you're approaching 0 from the right hand side on the x-axis, then your y value keep getting higher and higher and higher. So in the end, two directions did not agree. So allow me a minute to erase all this. All right, so putting it all together now at this point, left hand side on our function 1 over x, when we allowed x to get close to 0 from the left hand side, here's how our function behaved. Our function dropped to negative, vertically dropped, keep going down further to negative infinity. I do want to save all the graphical interpretation in a different video lecture. However, here in this problem, allow me to briefly explain. I hope anyone who comes to calculus here is well familiar with the graph of our 1 over x function. 1 over x function is a function like this. Okay. So as I was, and you can see my hand, my marker strokes right here as I was trying to get closer to 0, and you can see I was making my drawing from the left to the right. So as I was getting closer to 0 from the left hand side in my vertical coordinates, that's why it created this shape of the graph right here. But my y value, okay, dropped further down and dropped further down. That explains for our value, our y value drops to negative infinity. Okay, and on the other hand, for the right hand side, the same function, 1 over x, our limit of this function is going to be positive infinity as we were letting x get close to 0. You see, so if you are looking at how we graph that, if we're getting, so I purposely draw that in the way how you can see that as we were getting closer to 0, but from the right hand side, and our graph is rising up and keep rising up infinitely. And that's what explains for this. 1 over x has limits positive infinity as we were letting x coming close to 0. So in the end, the left-sided limits and the right-hand-sided limits did not agree again. So now we are ready to make our way back to the other board where we begin our problem. But making a final conclusion, our final conclusion on this problem, this function 1 over x, when x, the limit of 1 over x as x is getting close to 0, the answer is DNE. Okay, and remind yourself, DNE is short for does not exist. Okay, and of course I have to emphasize again and again throughout so many problems that we will never substitute. See, we did not do this. We did not substitute 0 into the function. We did not plug 0 into the function. We couldn't even do that since long time ago. Since we begin our learning in mathematics, then we were never able to substitute 0 into the 1 over x function. We can never divide by 0. I usually make a joke for all of my math students that the human on earth right here, we're famously for being stuck with dividing by a 0, divided by a 0 right here. Maybe unless one day we move to a different universe, then we have a way to handle how to divide by 0. But here on Earth, there's no luck for that. We've tried for so many years, but we still don't know how to divide by 0. Okay, so right in the beginning, we never divide by 0. The reason I mentioned here is that even as we're getting close to 0, take the limits for x getting close to 0, we got a DNE. So eventually, I keep having some students mistakenly giving this answer, f plug in 0 as a DNE. Nope, but this is the wrong way of answering your question. Now, remind yourself from algebra. F in this function, then plugging in the function value give you an undefined, meaning we don't have a value. We have an undefined value. We have an undefined limit, an undefined answer, an undefined output. I'm sorry if I accidentally set limits earlier, but substituting or plugging in 0 into the function, we could not divide by 0, so we have an undefined value, output value. Do not misunderstand that which does not exist. Don't use the DNE here. DNE is specially reserved for limits problem. So but in this problem, you do have a DNE limit simply because left-sided limits and right-hand-sided limits. See? Left-hand-sided limits and right-hand-sided limits did not agree. They went in different directions, and so in that way, our limits problem here is a DNE, a non-existing limit, but it has nothing to do. It's completely different things with having an undefined value. Okay, but that completes our lecture for now, as we're looking at limits under a numerical point of view, and especially numerical point of view means we're considering limits. We're finding limits completely based on the table of values, and we're trying to describe that we're getting closer and closer to a particular limit point.